Okay guys, so today we're going to start talking about polarity. This is one of the sections on the assignment that you received today in class. Now, what is polarity? So, what happens when a molecule is polar? You're going to have a difference in the sharing of the electrons between the bonded atoms. So, one atom is actually going to pull the electrons a lot closer than the other atom. For example, if you have a molecule of water, so you have H2O, this is the structure for H2O. The molecular geometry of H2O is bent. Now, what happens here is that oxygen is actually going to pull the electrons a lot closer to it. This leaves hydrogen with a partially positive charge. Now, this happens on both of these atoms. So because electrons are negative, if the oxygen is pulling more electrons closer to it, this causes oxygen to be slightly negative. Now, this is the molecule for water. This is what polarity means, is you have an unequal attraction for the electrons between the bonded atoms. Okay, some examples of polar molecules is polyatomic molecules such as water, the one I'm showing you here on the screen. The second one are like heteronuclear diatomic molecules. For example, if you have a molecule such as HF, so hydrofluoric acid also is a polar molecule. Why? Because here the fluorine pushes the electrons a lot closer to its nucleus. So therefore, you have fluorine, which is going to be slightly negative, and hydrogen, which is going to be slightly positive. Okay, this is very important because we're going to have to analyze the molecules that we have present in our worksheet. Now, some key notes to keep in mind is that highly symmetric molecules are normally nonpolar. Now, what do we mean by that, symmetric molecules? For example, you have a general formula such as AXN, where N can be equal to 2, 3, 4, 5, 6. So, as long as X is the same atom, these molecules will not be polar. For example, let's take CH4. If we have CH4, we have C. Oops, I apologize. So if you have CH4, even though we are going to have a difference in attraction of the electrons, notice that this molecule is symmetrical. What that means is literally if you can get the molecule, cut it in half, and you have equals on both sides, this means that the molecule is symmetrical. Now, this has to be perfect. You cannot split an atom in half, remember that. But if you have equal poles on all four sides of the carbon, you have no dipole moments, which means you're not going to be pulling those electrons any closer to any atom. Therefore, this is nonpolar. So this is a nonpolar molecule. And this usually happens a lot with symmetrical molecules. Now, some examples that you should keep in mind for polarity that are polar and nonpolar. So these are summary of molecular polarities for molecules having central atoms without lone pairs. So I'm going to make a T-chart here just to help you out a little bit better. This is nonpolar. Okay, so I'm going to put non-P, and then here it's going to be polar. Some of these molecules, so you're going to look at the molecular geometry. The geometry tells you a lot about the molecule. Usually, if it's linear, it is nonpolar. If it's trigonal planar, it is nonpolar. Tetrahedral, and I'm going to abbreviate some of these just to save space, it's nonpolar. Others include, let me see. Just going to erase that. Hopefully you got that down. Others include trigonal bipyramidal. So I'm going to put trig bipyramidal. And octahedral. Now, this list, you should have it based on that note that I gave you where it tells you what kind of shapes they are. Remember, we're looking at the molecular geometry for this. The molecular geometry helps us a lot. Now, for the polar side, you're going to have things such as, or molecular geometry such as bent. Okay, usually bent molecules are polar. So trigonal pyramidal. Okay. Square pyramidal. Okay, and like I said, I'm going to abbreviate some of these. It's just to save space, and so you can have more room. So I can have some room here to write. You're also going to have seesaw. So seesaw is under polar. T-shaped. Okay. T-shaped. Linear. And I know you saw linear on the nonpolar side, but we have to look at the linear shape of that molecule in order for us to understand that a little bit better. And square planar. So square planar. Now these are a good thing to put on your notes. It's going to help you a lot with figuring out the polarity of these molecules. Remember, polarity, just unequal sharing of the bonded electrons. So one atom is going to put those electrons closer to itself. Okay, so we have to look at our molecules to do that. For example, I gave you water, right? And water, we know has a bent shape. Now, bent shape was listed under our polar molecules. Therefore, it is polar. Now, you may think, well, the water molecule, actually, it can be symmetrical. So if you draw this, if you draw HH, you said, oh, well, what if we split it in here? It's symmetrical. And you said symmetrical molecules are usually nonpolar. That is true. But notice that the dipole moments that are pulling here, they do not cancel themselves out. Okay? They will not cancel themselves out. Now, if you have another molecule such as CO2, so if you have CO2, CO and CO2, so you have something like this. Now, the dipole moments, one's pushing this way, one's pushing this way. So they're both going to cancel each other out. This positive and this positive. Oh, I apologize. Now, I apologize because these should be slightly negative since this is pushing towards the oxygen atom. Okay. So because these are slightly negative, those dipole moments are going to cancel each other. Therefore, this molecule is not polar. Okay, it's very important for us to look at the molecular geometry of the structures. Okay, that's for polarity. Now, another thing that I want to make a note on is the violations to the octet rule. We had some examples today in class, and we have to know these. Now, I did mention in class that group 17 atoms are never ever going to have double bonds. Okay, never going to have double bonds. You had an example that was I3 to the minus 1. This minus is just going to tell us to add one electron to our mathematics. So remember that we have 3 atoms of iodine multiplied by the valence. There's 7 valence electrons. for every one atom. So for every one atom. So normally we would have 21, but we have to add that one electron. So plus 1, we should have a total of 22. Okay? So 22 valence electrons that we should have. So I'm going to go ahead and draw the molecule. And I know I said never put two bonds on a noble gas, but when in a halogen, but when the halogens combine, you're going to have to bond it to two things. Something has to be the center atom. So therefore I'm going to go ahead and draw my lone pairs around the iodine. Okay. Now notice if I go ahead and count my atoms here, or my electrons, I'm sorry, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 pairs. Okay, so 10 times 2 is 20. This becomes a problem because my mathematics said that we should have 22. Okay, when this is the case, what you're going to have to do is you're going to have to add those lone pairs to the center atom, even if it has more than 8. So now I'm going to have 8 electrons. I'm going to have 10 electrons around that center atom. Okay, and I know that violates the octet rule, but there's some exceptions that can violate the octet rule, and this is one of them. Now, another exception that can violate the octet rule, for example, is if you have something like BF3, okay? So, if you have BF3, let me go ahead and draw that molecule here for you, BF3. Okay, if you do the math, you're going to get 3 plus 21, which is going to give us 24. So we should show 24 valence electrons. Okay, so we know that fluorines can never make a double bond, so I'm just going to go ahead and I'm going to bond the fluorines here. And I'm going to go ahead and draw those lone pairs for fluorine because it can't make a double bond. So I have to add those lone pairs. Okay, if we count the electrons now, okay, so let's go ahead and circle the pairs. So I have 1, 2, 3, 4, 5, 6. Remember the bond counts as 2. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 and 22, 23 and 24. Well, we matched our 24. There is a problem though. If we look at the boron in the center, it does not have 8 electrons. Okay? This is another exception to the octet rule. Okay? This boron, what is boron and indium? They both can have 6 electrons around them and they're happy. They do not need to have 8. Okay, these are some examples that were given to you on the worksheet. I hope you can work out through the worksheet now. Now you know on polarity, you know how to solve for the molecular geometry and how to solve all the problems that are listed there for you. If you have any questions, feel free to write them. Please ask me at the beginning of class.